Let's look at the next example. I want you to work on this for a few minutes on your own. It's very similar to the previous example, except now we have this piecewise function. So again, answer the question, where is f continuous? And that might take a little bit just extra work to figure out. And then for part B, at each value of x where f is discontinuous, can you redefine the function to make it continuous? So the strategy here is exactly the same as the previous problem, right? Where does the function have the direct substitution property for part A? And you might have to deal with this x equals 0 separately. And then for part B, try to figure out how you would define f at each of those discontinuous points, or points of discontinuity, I should say. So let's set aside, say, 3 minutes and some change for you to write as much as you can for that problem. All right, let's look at the solution. So what would you say is the answer to part A? Where is f continuous? Okay, so it looks like we got three different answers, but they're really all the same. So Abigail gave us the answer in interval notation. Anton gave it to us in English, everywhere except when x equals 0, right? So minus infinity to 0, meaning 0 to infinity. Okay, so everywhere except 0. So can you, first of all, now did you write down a complete or work or complete justification for this? So first, I want to remind everyone, you know, how do you determine where something is continuous? That's the same thing as asking where does f have the direct substitution property? Now everyone is saying except 0. So here's a question. Did you only check continuity at 0, or did you give a justification for the other values of x? For instance, why is this function continuous at x equals 3? Did you give a justification for that? Did anyone happen to do that? Did anyone happen to give a justification for values of x other than 0? Anton, you didn't. I imagine most people may have skipped that part, right? It almost seems kind of obvious. So let's actually write down a brief justification. So I can say, what do I know about each of these pieces? X squared plus 3 and x minus 5. Each of those pieces are polynomials, right? So those pieces individually are continuous. We know that with piecewise functions, as long as each piece itself is continuous and those two pieces meet up at the transition points, in other words, there's no jump discontinuities, then the function actually is continuous. So let's write that down as a brief justification. So each piece of f has the direct substitution property, right? X squared plus 3 and x minus 5, they both have the direct substitution property. So automatically I can say this function is continuous everywhere except possibly where those two pieces attempt to meet up at the transition point at x equals 0. So the only value of x for which we are initially unsure continuity is x equals 0, transition point. I imagine a lot of you may have not justified your answer for x not equal to 0 because you may have thought it was automatic, and that's fine. I mean, x squared plus 3 and x minus 5, you should get to the point where you automatically realize that those functions are continuous, right? Okay, so let's actually check. Um, so to check whether f is continuous at x equals 0, we must check whether what is true. We need to check that primary condition for continuity, right? Is the limit as x approaches 0 of this function equal to f of 0? Now, what does this mean, in practice? What does this mean in practice? I need to check three things, right? This tells me that there are three quantities that in general have to be equal at a point for that function to be continuous there. Right? What are those three things? The left limit, the right limit, and the function value, right? Because if the left limit and right limit are equal, that means this limit exists and is equal to that. And then that itself has to be equal to f of 0. So three quantities have to be equal. And that's how we're going to kind of emphasize continuity a lot, right? Three quantities have to be equal at that point. The left limit, the right limit, and the function value. So let's do that here. Let's do it formally. Even though the calculation isn't too difficult here, let's do it formally. So f of x, sorry, the limit as x approaches 0 from the left, I would need to use the piece x squared plus 3. I substitute and I just get 3. Now 0 from the right. I have the piece x minus 5. I get negative 5 as my limit. And then I would also need to, now at this point, I already know that the function is not continuous, right? Because these two numbers are not equal. But just to, for the sake of it, let's just actually also complete this with f of 0. So for f of 0, notice for 0, the equal sign is on the second piece. So I need to substitute 0 into the second piece to get the value of f of 0. So x minus 5, and I put a line here to mean I'm putting in x equals 0. And that's negative 5. So now I look at these three numbers. They are not all equal. Right? The left limit, right limit, and function value are not all the same number. So therefore, the function is not continuous. Right? So I can say, in particular, the left limit and right limit are not the same. So f is discontinuous. Okay, so then in summary, I can write f is continuous on the set that a few students had written earlier. Minus infinity to 0, union 0 to infinity. Questions about that? Any part of that justification? So here's a question. What if a student only checks the first two numbers? And let's say in this case, they didn't get 3 and negative 5. They got 3 and 3. And the student then concludes, okay, the limit from the left equals the limit from the right. Therefore, the function is continuous. What is wrong about that explanation? So I'll say it again for anyone who missed part of it. So the student calculates the left limit and the right limit, and they calculate that both of them are equal to 3. And so they say the left limit equals 3 and the right limit equals 3. Therefore, this function is continuous at x equals 0. What is wrong about that justification? We don't know if it's a hull. So that is true, but let's get a more precise reason why that is an incorrect justification. It is true that there could be a hole in the graph, and that's the reason why he's wrong. But let's be more precise about that. They didn't check to see if the limit equals f of c. Nicole, if we don't calculate f of x, there could be an error if it doesn't equal to the left or right limit. Okay, good. So that's what I'm looking for, right? The left and right limit, checking the left and right limit are equal is not enough because those two numbers not only have to be equal to each other, they also have to be equal to the function value. And like Abigail said, if the case is that the first two numbers, the left and right limit, are equal, but the third number, function value, is not equal, then yes, you do get a hole in the graph. But just to say, oh, there could be a hole in the graph, that's not really the proper justification. Okay, good. So in fact, checking the first two only, checking left limit and right limit only tells you whether the limit exists. It does not tell you continuity. Continuity, you need that one little extra piece. You need the fact that that limit exists and is equal to the function value. Okay. All right, good. So now for part B. At each value of x where f is discontinuous, can we redefine the value of f so that f is continuous there? How did you go about solving part B? Okay, so Prathana says no. In other words, it is not possible to redefine f of 0 because the left and right limits are not equal. Okay, good. That's kind of the most concise way you can justify this. So now let's write it all out kind of in full detail. So again, to remind you, what is the question really asking? I want to just rephrase it until you're kind of used to it. So can we redefine f of 0 so that f is continuous at x equals 0? That's what the question is asking. And again, let's note what this actually means. So note, the only choice for f of 0 is f of 0 would have to be equal to the limit as x approaches 0 of f of x, right? That is the condition for continuity, right? That the function value equals the limit. And now, as Prathana said in chat, well, this limit doesn't exist, right? Because the left limit and the right limit are different, right? 3 and -5. So if this limit doesn't even exist in the first place, well, then there is no candidate choice for f of 0, right? So it's impossible to make this equation true if the right hand side doesn't even exist in the first place. So since the limit as x approaches 0 does not exist, it is impossible to redefine f of 0, make f continuous at x equals 0. And what kind of discontinuity do we have in this case of those four types that we talked about? So remember? So in this case, I have a left and a right limit that don't equal each other. What kind of discontinuity was that? Jump, right. So let's see. So let's graph this. So x minus 5, oh, no, x squared plus 3, and there's an open hole there, and then x minus 5, and there's a closed hole here. So this is what the function looks like, right? So we can see, is there any place that I can kind of fill in a hole to make the function continuous? So you can imagine kind of, here's a filled in hole. Is there anywhere at x equals 0 I can place this function value to make the function continuous? Can I put it here, this open hole? Or can I put it here, this closed hole? No, there's no way to redefine, right? Because you can see that no matter where you put this function value, these two pieces, right, this straight line, this parabola, are never going to meet up because of that jump. So there's no way to put this function value somewhere.